There we go. That would help if I had my announcement slides set up in advance. Okay, we are on lecture 18. How did the last homework go, the force couple assignment?
The second problem was not it.
A little tricky?
Yeah.
Well, I think this one will be easier, if it makes you feel better. Yeah, so yeah, here's the other thing I'll say. 3-7, which theoretically should be harder, I get this weird feeling isn't going to be. I think that's actually going to be an easier assignment. Because I think that the thing with force couples is you're trying to do shortcuts. So with 3-7, we're not, and maybe just barreling through and doing it might actually make it an easier assignment. But we'll get to that here in a bit. Today what we're going to do is broach what I think is one of the really critical topics in this class, which is equivalent force systems. You recall last time that I said that if you're in an algebra class, for example, and you're given a problem where you need to take a mathematical expression and reduce it into more manageable terms, and you had an equation that had, something like this, what have you, plus 5x, that you'd have all these terms and you would collect them into a single term, right? You wouldn't deal with all five, it wouldn't make any sense. You would take it and you would resolve it. In statics, and in engineering systems in general, we have problems where we have a system subjected to oodles and oodles of forces. And what we want to do is reduce that into a more manageable set of vectors. And so in order to do that, we need to take force system 1 and turn it into force system 2. And we need to do it in such a way that these two systems are equivalent. So what does that mean? Okay, and that's what we're going to talk about today. Did everybody get the code? Okay, so this is, again, a critical topic, but I want to be very, very crystal clear in this latter point here. So, like I said, we're resolving a system of forces into a smaller, more manageable system. And the way that we do that is we recognize that the sum of the forces in system 1 must equal the sum of the forces in system 2. Likewise, the sum of the moments in system 1 must equal the sum of the moments in system 2. The same thing was true when we were dealing with particle statics. We just didn't have to deal with moments. I mean, remember like one of the classical problems we had in exam 1 land is I'd give you a hook or a bracket, and I would say, here's 5 forces on it, turn it into a single force. And the way that you would do that is you just add them up, right? And you would get a resultant, right? And the idea is that we could replace those 5 forces with this single resultant, and it would be statically equivalent. Well, we're going to do the same thing, only now we have to also consider moments. Now this latter box here, this is really important, okay? So to simplify systems, we're going to sum the forces and sum the moments, but we're not yet dealing with equilibrium, okay? So for right now, we're not taking this sum and setting it equal to 0, okay? We're going to do that later, okay? But right now, we're just adding everything up, okay? So far, so good? Okay. Now, in order to illustrate how this works, I think the easiest thing to do is to just deal with the problem, okay? So this is going to be our focus for today, okay? Let me bring up the notebook. This is our focus for today, okay? This is all we're going to talk about, okay? So I have 4 tugboats, and they're exerting pressure on this like barge, this cruise ship, okay? And the idea is that these 4 boats are trying to bring the ship to the pier, like bring it to dock, okay? So what I want to do is I want to determine an equivalent force system, but also if I wanted to replace these 4 boats with 1 boat, where should that boat be in order to generate the same forces and the same moments as all 4, okay? So a couple things that I want you to recall as we start going into this, okay? So the first thing I want you to recall is we can shorthand this as what? One kip. Yeah, sorry, I didn't state that properly. Like we can reduce that and say that 1,000 pounds is equal to one kip, right? And so the reason I'm saying that is because these 5,000 pound boats, I'm going to say that instead of the magnitude being 5,000 pounds, I'm going to say that the magnitude is 5 kips, okay? And my reason for doing that is just to make the numbers a bit more manageable, right? Because if I'm taking like the number 5,000 and multiplying it by 200 feet or 100 feet or 500 feet, suddenly I've just got really, really big numbers, right? And so if I can take those numbers and sort of squunch them down a little bit, that's going to make my life a little easier. So I want to do that part first, okay? The other thing I wanted to mention is, does anybody notice something about the 3D aspects of this problem? There aren't any. This is a 2D problem, right? Okay? So remember that moments in 2D, remind me, what's the deal with moments in 2D? How about this? Does this ring a bell? Does that ring a bell? In other words, like one thing we could do is just this, that Rxfy minus Ryfx. We could just deal with those terms. So, like, this is a really, really important point, bless you, because if we recognize this, we can avoid this. Because, like, if you want to do a 3x3 determinant for every cross product in the system, go right ahead. I have a nice little plug and chug equation that I can use to determine cross products right here, okay? So I'm going to evaluate my cross products using this, okay? I want that to be relevant as we start going, I wanted that to be readily apparent and relevant as we start doing this problem. Okay. Okay, so we have 1, 2, 3, 4 boats here on this ship. Okay, these 4 boats. What we're going to do is we're going to focus our problem around point O because we're going to try and determine the equivalent force system about point O. So how are we going to do that? Okay, so the first thing that we're going to do let's do it like this. Write each individual force vector in IJ notation. Okay. So let's do that part first. Okay. Let's start off with F1. Let's go back a ways. F1, remind me, what's the magnitude of that force? 5,000 pounds or 5 kips, right? Okay. Is the X component going to be positive or negative? Negative. The X component. Like here's F1, right? So we're looking at F1, right? So if this was my coordinate system, F1 is going to be pushing like that. So the X component is positive. The Y component is negative. So can't we do this? Can't we say Isn't that the description of that force vector right there? Isn't that how we did it old school? Magnitude times a cosine, magnitude times a sine. Don't forget the magnitude inside. And keep in mind that the units are in kips. So 5 times the cosine of 60. The cosine of 60 degrees is a half, right? So a half times 5 is 2.5. And then minus, I'm not that good. Sine of 60 degrees is a little messier. Square root of 3 over 2 times 5 is what? Okay. Is that fair? All right. So let's keep going. Now, let's talk about F2. Okay? Now, notice how F2 is written in this like 3, bless you. Notice how it's written in this like 3-4 slope ratio, right? So if it's 3 and 4, what's the hypotenuse? 5. Okay. All right. So here's what I'm going to do. I'm going to say and just put the units here on the outside. Now, I haven't yet figured out what the cosine of these angles are, but everybody with me on this? Okay. Now, you do not need a calculator to figure out the sine and cosine of this angle. Okay? Let me show you why. So, I'm about working smart, not hard. Okay? So let's break out my little thought bubble over here. So I have myself a right triangle. This is 3, this is 4. Bless you. All right. Now you all told me this is 5, right? Okay. Now, one way of doing this problem is to say, okay, Dr. Mike, we need, tangent of theta is 4 over 3. So therefore, theta is inverse tangent of 4 over 3, right? That's what you're telling me, right? Don't do that. Don't do that at all. Instead, we're going to go back to basics. Let's go back to basics. What is my goal? I don't really care what theta is. I don't care. I care about what the cosine of theta is and what the sine of theta is. I propose that the cosine of theta is 3 over 5 and that the sine of theta is 4 over 5. Why get an angle by taking an inverse tangent and then take sines and cosines of that angle when I could just use this? I propose that we can just say we can just do this. A lot of magic in this acronym. A lot of magic in it, okay? Make your life easier. Now that, I don't think that's going to work for like this or 60 degrees, but same idea, right? Does that make sense? Now what about F3? How are we going to describe F3 as a vector? How are we going to describe F3? Negative 5 what? J, because it's going downward. 0i and 5j. So notice how I'm writing this KIP unit over and over and over again. I'm going to organize this here in a little bit in a nice little table. Okay. Now for F4, F4 is going, well, what's the X and Y terms? Are they going to be positive or negative? Positive, because it's going up and to the right. And my angle is 45 degrees. So for F4, okay, and the cosine of 45 degrees and the sine of 45 degrees are equal, so I can just do one of them. And cosine of 45 degrees times 5 is, what was it, like 3.536? Not like that? So, okay. That's not bad, right? So notice how if the goal is to compute moments, what do I need? Rx, Fy, and Fx. For every vector, I have, here's Fx, here's Fy, here's Fx, here's Fy, Fx, Fy, Fx, Fy. So now all I need is an R term, an R vector for each one, and I'll be able to do these cross products pretty systematically, right? So let's write our position vectors, okay? So now what we're going to do is we're going to determine our position vectors. So we're going to determine the position vector from the point in question to each force. Let me see if I can cheat a little bit so I don't have to keep scrolling up and down. Are you kidding me? Try this one more time. All right, never mind. It doesn't like me. Okay. Sometimes OneNote's a little weird like that. Okay. So we'll try and restrain our scrolling as much as we can. I'll use the board a little bit and then I'll transpose. Okay. So let's see if we can figure out from point O, because that's our point in question, from point O, how far do we have to transverse to get to force 1, to force 2, to force 3, to force 4? So let's take force 1. How far do we go on the x-axis horizontally? -90. How about the y-axis? Is it 70? Now hold on, look right here. 70 is on the top, but force 1 isn't quite on the top. So it's 70 feet here, but there it's 50, right? So this is going to be 50J. Does that make sense? What about force 2? Here's point up, okay? How far along the x-axis? 100 on the x, positive, right? What about along the y? 70. See what I'm doing? R3 is going to be what? Tell me what R3 is. 400I and 70J. And then R4 is and negative 70J. Does that make sense? Everybody okay with that? And these are all in feet, right? So again, we're going from the point of origin to where each force is. Okay? So I'll just transpose these down. And these are in feet. Okay. That's not too bad, right? Okay. All right. Now what we're going to do is we're going to look at our equivalent systems. Okay? Now, I propose that two systems are equivalent if they have the same sum of forces and they have the same sum of moments. Okay? So here's what we're going to do. We're going to evaluate R cross F for each force and then sum all forces and moments. So we're going to evaluate the R cross F for each one and then sum all forces. I am an engineer, okay? So I like tables. So let's see if we can draw us up a table. Okay. So there are 4 boats, right? So okay, so let's start off by rewriting all these R vectors. Again, I'm sorry for all the rewriting, but I just want everything here in one spot. So the R vectors, we have negative 90I plus 50J. We have 100I plus 70J. 400I plus 70J, and then 300I minus 70J. Okay. Next thing I'm going to do is I'm going to write down all these force vectors. Okay, let's see what I had. I had 2.5i minus 4.330j. I had 3i minus 4j. I had 0i minus 5j. And I had 3.536i, and then the same j. Okay. So now what I'm going to do is I'm going to do R cross F. And my answer is going to be in foot kits, right? So for each row, I'm going to be able to do a computation. So maybe for this first row, what we'll say is that's going to be M1, which is R1 crossed with F1. But how are we going to do that? We're going to use this, right? Rx Fy minus Ry Fx, right? So what is Rx Fy minus Ry Fx? So I'll just put down here on the side, note M1 is going to be 2.5 times what? 50 minus negative 4.330 times 90. Did I get that right? Negative 90. Did I get that right? Did I do that right? Oh, it's backwards. It is backwards. Whoops. I'm trying to... Yep, that is backwards. I was like, something didn't feel right. So negative 90 times negative 4.330 minus 50 times 2.5. That's how I'm going to do that. Yeah, something didn't feel right. What are we getting for this? Okay, so from a vector perspective, that would be 264.7 K, right? Because remember, in X and Y, the vectors all spin about the Z-axis, right? Or the moments all spin about the Z-axis. Okay. So, let's see if y'all can help me out with this. What are we going to get for M2? Say it again. Do I have a second? Okay, what about M3? And what about M4? $1308.1. Is that what you said? 0.32. We'll call 0.3. Second? Okay. I'll put this in my little thought bubble. And maybe what we do to be hyper accurate is that. Okay. Okay. Now, like I said, what we're going to do is we're going to sum these forces and sum these moments. So you could probably see I left myself a little space here on the bottom. Maybe I'll squinch this a bit. Okay. And then what I'll do, put a little summation here, row down here. So let's start off by summing the forces. If I sum these vectors, like Well, how do we do that? Well, we sum up the I terms, sum up the j terms. So what do we get when we sum this up? So we'll get a resultant vector. And what is that? We'll say 2 decimal places on this. We got the x term, 9.04, and then minus j is second on that. Okay. And how about my moments? What happens if I sum those? Maybe we'll call this MR, my resultant moment vector. 1037, is that what you said? I got 0.2. Did you get what'd you get for the? We'll call it 1 decimal place. You didn't get 1? Okay. Negative 1037.0. Second?
Yes.
Okay. I think I did it in Excel, so it was tracking some of these decimals a little differently. This is close enough. All right, is everybody good with this? Okay. Now, what do these 2 vectors mean? Okay. So, here's what these mean. Has everybody got this? All right, can I scroll up to the top real quick? Okay. So, this is what I'm going to do. See this right here? I'm going to call this system 1. Okay? So I have a rigid body, in this case the barge, and I have 1, 2, 3, 4 boats on that force. So I have 4 forces. This is system 1. Okay? I propose that I'm now going to create another system, which I'm going to call system 2. Okay? And here's what system 2 is going to look like. And please forgive my horrendous art. Okay, again, my apologies. That's the best barge you're going to get. Okay, and here is point O. Okay? I propose that this system, I'm going to kick all those boats off, and I'm going to replace them with 2 vectors. The first vector is what I'm going to call R. Which is so instead of 4 vectors, each with a magnitude of 5 kips, I'll have this vector with whatever its magnitude is. We can figure that out pretty easily, but I'm not really worried about that right now. The second vector is not going to be a force, it's going to be a moment. And that vector is going to be a moment vector. Now, why am I drawing it clockwise? Because the moment's negative. It's 100% right. The moment is negative 1037, so I'm drawing it clockwise. And this is going to be moment that. And this is one of my answers, but I'm going to call this system 2. And I propose that system 1 and system 2 are statically equivalent. Why? Because here, like, look at this table. That, and that. That's all the forces in system 1. This, that's all the moments in system 1. This resultant vector is the sum of all those forces. This resultant vector is the sum of all of those moments. So if I get rid of all those, replace it with this, these systems are statically equivalent. Does that make sense? Okay. Now we're not done with this problem. We got a little bit more work to do because I'm going to come up with system 3. Okay? But I want to, before we get to system 3, I really want to make sure that system 2 makes sense. Everybody okay with this? Any questions? Okay. All right. Can I scroll back up since OneNote doesn't like me? All right. Okay. Now I want to read this this question here because I think without having done the work so far, this second question would seem really complicated, but it's actually not. Okay, so let's take a look at this question. So first off, I need to improve my grammar because that's a question, not a sentence. So I forgot a question mark at the end of that. Whoopsie. That's supposed to be a question mark. Okay, now, where should a single, more powerful tugboat push the ship to produce the same effect as the original 4 tugboats? Okay, let's digest that a little bit. Let's start off with single, more powerful tugboat. What do you think it's talking about when it says a single, more powerful tugboat? Say it again. That's 100% right. It's talking about R. Okay. Where should we put R to generate the same effect? Okay. And one of the key things is the term push. Notice how in the problem the tugboats are pushing with their tips, sort of pushing the boat. Okay, so I want to take a look at system 3. Okay, and again, my sincere apologies for my horrible sketches. Okay. Again, I'm really sorry. That's a ridiculous sketch. Okay. Now, the next thing I'm going to do is I'm going to draw this sort of midline point right here, or the midline through the barge. Okay, and I'm doing that because what was this distance right here? What was that distance? It was 70 feet. That was 70 feet. Okay. Here is, oh, that's point O, right? Okay. Now, remind me, which way does the resultant vector point? It points down like this, right? So the problem said, where do I put that tugboat to generate the same response? So I'm going to put that resultant vector right there. Okay. The problem is asking, where do I put it? So maybe what I need to figure out is Maybe I need to figure that out. How am I going to figure that out? Well, here's how I'm going to figure it out. Okay, I propose that's system 3. For systems to be equivalent, they must have the same sum of forces and what? Sum of moments, right? So how are we going to determine the moment that this force generates? Well, we've got the force, we need an R vector, right? So I propose the R vector I can draw that better. That's better. That's the R vector. So let's describe these. So my force vector is 9.04I minus 9.79J, and that is in kips. Somebody describe the R vector. What is the R vector? Like, is the X component positive or negative? Positive. It's going to the right. Is the Y component positive or negative? What is the X component? It's my unknown. What's the Y component? 70. Okay. So, what is R cross F? In this case, or little r crossed with big R. Like, how do we do that? Well, we say it's Rx times Fy. Yes?
Would the 70 and the little r be negative? Or
no? No, because from here to here, we go up 70.
Oh, okay. I was thinking it was on the bottom. That's not.
Yeah, no. It's it's right here. Yeah. So this is going to be X times Rx times Fy minus Ry times that. Right? That's the cross product. And if we evaluate this, what do we get? We get negative 9.79x minus, what is that? 7 times 9 is 63, 632.8. Oh. Brackets, wrong place. Okay. What do I do with that, though? There you go, right? Because this, R cross R, must equal that, right? So, and what do we get for X? Say again? 41.29, so maybe call it 41.3. Do I have a second? So, system 1 had a bunch of votes. System 2 had 2 vectors, a force vector and a moment vector. System 3 only has 1 vector. There's only 1 vector in system 3. We just put it at this very magical spot. Where do we put it? Wherever it needs to be to generate the same amount of moment. So I propose that if we got that 1 boat out there and pushed it right there, it would be doing the same job as all 4 of those boats together. Why? Because this vector has the same sum of forces as all those other boats, and putting it right here contributes the same moment as all of those other forces. Does that make sense? Yes.
In the beginning, how do you know where to put the force vector?
What do you mean, like right here?
Yeah, how do you know to put there?
Well, so that's a good question. So I'm putting it on top because if this was a boat, okay, all right, so here's why I'm doing that, okay? You agree at this point that the vector is pointing this way, right? It's pointing that way, right? So I'm putting it on the top because if I look back at the problem, all the boats are pushing it, right? And so if I put it on the bottom, it would be pulling, right? So I just put it on top because that's where it would be doing what all the other boats are doing. There's no hard and fast rule that says I couldn't put it down here, but then it wouldn't be a push boat, it'd be a tugboat. So, well, actually, no, it is. Maybe I need to come up with a different term. So, because I said tugboat there. No, but I'm putting it on top just so that it mimics what all of the other boats are doing. But the whole point of the problem is, like, how did I know to put it there? I'm actually trying to figure out where to put it. That's the whole point. So
could it have that down the resultant vector? Could it have been more to the right or more to the left? And you just solved for the x.
Well, here's what I'm saying. If I put it right there, it would not generate that much moment. This is the only place I can put it to generate that much moment.
Just to draw it.
Oh!
Just draw it.
Yeah, that's fine. Yeah, I get what you're saying. That's fine. All right, hold on. We have one question.
So when you're writing the answer, it asks where to put it. Would you also need to put the y coordinates right in the point coordinates, or would you just need to write the x coordinates?
That's a great question. For this problem, I don't really think it's necessary because the configuration of the barge is that it's 140 foot wide, 70 foot on each end. So you know that this is going to be 70. So really the only unknown for this problem is what this is. But if you were to write the answer as 41.3 comma 70, I wouldn't be upset at that at all. So let me put it like this. The homework assignment, what I'm giving you is a big trust problem, and you're being asked something very similar, where to put a load on the bottom of the truss. And so it's going to be, I think the homework even says express it as some distance to the right of this. So it'll be x equals whatever. So. Sound good? All right. I'm going to pull up the code one more time. I'm not giving you any more time, though, because it's right at 11:50. I'm sorry. I'm not giving you any of your life back today. But this is a good problem. So we'll see you.